Hi, my name is Isaac Haynes, and I'm here to talk about how ferric iron catalyzes the formation of iron-rich silicates under Archean-like ocean conditions. To understand Archean ocean conditions, you basically need to look at the deposit that's from that time to understand the ocean seawater conditions at the time. So here we have abandoned iron formation, which is reflecting that time. And what we see is these iron oxide-rich minerals in red, followed by the silica-rich minerals in white. And inside those silica-rich minerals, we have things like chert nodules. And when we look inside of a chert nodule, basically helps preserve the thought to be precursor minerals of the time that actually precipitate in the ocean and sea washing conditions and reflect non-altered products. And what we notice in those are presence of a mineral of a rhenolite, which is an iron silicate, which is 7 angstrom spacing by TEM. And basically what this hints at and what our project goal then turned into is what are the conditions necessary for an iron silicate like rhenolite to form under Archean-like seawater conditions? How does the pH influence the formation of iron silicates? What impact does the presence of iron 3 have on iron silicate formation? What phases and morphologies are present across these different pHs with and without iron 3+? Where our solution chemistry is an artificial Archean seawater that has 1 millimolar silica and 1 millimolar iron total, where it's either all ferrous or it's ferrous plus 5% ferric iron across a pH range of 6.5 and 6.5 to 7.5. So let's take a look at these precipitating materials. So across our different ranges shown here in this top panel is the ferrous cases. We're seeing very little precipitation up until pH 7.5 with a little bit of precipitation shown here. And then when we add 5% total iron as ferric iron, we're seeing this kind of orange to green textures and so much more material produced, which is really incredible. And it's reflected by the mass data shown to the right here. Now, what's actually going on the nanoscale of what we're precipitating? Let's take a look at TEM, transmission electron microscopy, where basically if A through C, what I'm showing was the bottles of pH 6.5 at room temperature. And what we're seeing is a largely amorphous character in general, as shown by the selected area diffraction in the bottom right. And then when we zoom in on certain little areas, we've seen a few indications of basically 7 angstrom iron silicates at pH 6.5 versus when we're at pH 7 and kind of D through G at room temperature, we're also seeing very amorphous materials in general with possibly hinting at the presence of an iron silicate, but we can't tell. So then what happens if we age these products A and D at 150 C to understand what else could exist and crystallize out of this. So what we're seeing at pH 6.5 and H after being heated is a variety of different phases shown here in I, where we're seeing kind of these triangular shapes, the amorphous, to these layered structures. Then you can see better in J and K, where we really want to look at the extensive formation in these nice 7 angstrom clays, okay, surrounded by iron oxides as well. So then we look at N, which is pH 7 at these heated conditions. We're also seeing a variety of different phases, but there's these large layered crystalline iron silicates again in P and Q that are also 7 angstrom in spacing, which is just incredible to see that we're actually forming these 7 angstrom iron silicates under these environmental conditions. So what happens if we take a case where we don't have any ferric iron? So that's shown in this top row where we have 0% iron 3 at pH 7.5, where we have heated it. So what we're seeing is very largely amorphous character in the background. And then we're also seeing these clumps of poorly ordered structures in C through F, where basically they're hinting at kind of iron silicate clay-like structure, where we have one example where we possibly have layers of 7 angstrom, but these are very, small occurrences. But this is at pH 7.5. So this brings up the question, okay, well, maybe it's pH that's really controlling this. So then we look at all the other pH with ferric iron incorporated, and that is the room temperature experiment shown in this middle panel, and basically the heated experiment in this bottom set of panels. And what we're noticing in both sets at pH 7.5, heated and room temperature is a very poorly ordered structures in both cases. And we're seeing that basically we're not forming these beautiful clays like we were, or iron silicates like we were before. But when we do heat it, we are kind of hinting that the structure as shown in U of these structures may be closer to 7.9 or slightly higher. And so we want to see how this kind of pairs up to a bulk state when we look at something like XRD. So when we look at something like XRD, we're seeing this overall room temperature amorphous signatures followed by across all pHs, versus then when we go to pH 6.5 and 7 that are high temperature, we're seeing specifically over here in these earlier 2 theta ranges, we're seeing the presence of peaks that are overlapping with 7 angstrom clays, which is awesome to see that, you know, corresponding with the TEM data that we had, surrounded by a variety of different iron oxide minerals shown here in standards. But then at pH 7.5, even the high temperature, we're not seeing the presence of this, we're lacking that 7 angstrom clay spacing in both cases in a variety of different places on the diffraction, which is very kind of unique, showing that pH has something to do with this. So what we kind of broad conclusions we can make is that ferric iron can catalyze 7 angstrom iron silicate formation at lower pHs, 6.5 and 7, which produces something similar to what we think is crostitite or greenolite under environmentally plausible ancient ocean conditions. And that pH is an important control on iron silicate formation, as shown by our pH 7.5 experiments with 0% ferric iron and 5% ferric iron, where we're making those poorly formed structures. So the next steps of this is to basically investigate how aging at different temperatures and timescales can affect the crystallinity of 7 angstrom iron silicates. So I want to thank you for joining my talk, and please ask any questions you have about my project. Thank you very much. All right, bye-bye.